Okay, let's start. Good morning and good afternoon to all the participants. Welcome to the Trillium webinar entitled Introduction to Centrifugal Pumps. The webinar will be 1 hour long, divided into 45 minutes of explanation and 15 minutes of question and answer. Please use the chat channel to post your question, and we will answer at the end of the webinar. The webinar is presented by me, Luigi De Franco. I hold my bachelor degree in mechanical engineering in 2K4, and I have 18 years of experience in the industry. I'm working as fluid dynamic design manager at Trillium Flow Technology in La Spezia, Italy. My skills mainly span the field of fluid dynamics design and CFD analysis.
Hello, everyone. My name is Alan Ortega. I currently work as a project engineer under the Trillium Pumps USA division in Fresno, California. My experience at Trillium spans designing engineer-to-order projects and project management. I hold a bachelor's degree in mechanical engineering, and I am also a registered professional engineer in the state of California.
Okay, starting with a brief overview and background. Trillium Flow Technology is a global company that provides a broad spectrum of pumps and valve solutions to meet our customers' needs. We support our customer with a global sales organization and have multiple manufacturing sites around the world. A few of the pump brands that we will cover today include Flowwave, Gabioneta, and Thermomechanica pumps. Trillium Flow Technology has a long heritage of innovation over 190 years. The three pump brands being discussed today being Flowwave, Thermomechanica, and Gabioneta were respectively founded in 1934, 1912, and 1897, representing a wealth of experience and capabilities. Trillium is continually adding new products and services to make our customer processes more efficient and productive. In 2020, we added red point valves to the Trillium family, and in 2021, we welcomed the Thermomechanica Pompe to the Trillium Flow Technology family, further broadening our capabilities to offer solutions to our customers. These slides show different pump type designation as defined by Hydraulic Institute and API standards. In the first row, we can see the overhanging impeller that are designated OH1 to OH6. The second row describes the between bearing pumps from BB1 through BB5, and the vertical suspended pump from WS1 to WS7. So the content of the webinar are mainly reported on this summary. Initially, we talk about the definition of centrifugal pumps. Next, we will make a description of the main parts of the centrifugal pumps. After, we will proceed with fundamentals of centrifugal pumps, and we will move on the description of how to read the performance curve. At the end, we will make a description of the basis to consider to select the centrifugal pumps. And the final section, that covering the last 15 minutes of the webinar, will be dedicated to Q&A. Please feel free to enter your question in the dedicated chat, and we will read all your questions and we will answer. So let's start with the scheme of what is a centrifugal pump. What is a pump, or better? A pump is a machine that moves fluids, mainly in the fluid state or with partial gas content or slurry, from a low energy point to a high energy point, through the conversion of an energy source that is usually mechanical. The pumps operate through some mechanisms that are usually reciprocating or rotary, that require mechanical work to move the fluids. The pump can have very different sizes, ranging from the microscopic, as you can see in the figure on the left, for medical use, up to very large industrial pump, as you can see in the image on the right, that is relative to an NV pump type, that can handle over 70,000 meter cubic per hour flow. In a very generic way, it's possible to divide the pump into two main macrofamilies, the positive displacement and the centrifugal pumps. Okay, let's now describe the basic principle of the operation of a centrifugal pump. The fluid entering the suction inlet of the pump is conveyed into the rotating part called the impeller, which, through the action of its blades, move the fluids towards the outlet section, gaining total energy. The high dynamic component of this energy must be converted into pressure energy, partially, through the reduction of the absolute velocity of the fluid. And this occurs in the starter components that are volume of diffusion. In the animated image that you can see on the right, you can see the motion of the pressure distribution from the impeller inlet to the volute outlet. Blue color refers to low pressure, while red color refers to high pressure. This is a CFD analysis that we usually made in a drilling flow. Now let's talk about the main part of the centrifugal pumps. Here there is an example of a OH2 pump type. It's an overhang impeller with a single suction. We can find the rotating part that is the impeller, and the casing with the suction flange, that is the inlet section of the pump, and the discharge flange, that is the outlet section of the flange. We can see also the wear rings elements that are in the rear part, in this case, and in the front part of the impeller. We have the rear cover, and we have also the wear bearing housing and the truss bearing. So in the next part, we will focus on the hydraulic part of the pump. The impeller is the rotating part that transfers energy to the fluid and can be dropped on open impeller on the left, semi-open impeller, and enclosed impeller on the right. The first solution has only a partial disc on the rear of the channel, and the external part of the blades are partially cantilevered. The second solution has the inner disc completed, covered by the blades, and this is called the hub. This is called the hub, while the last solution has both the hub and the shroud, that are the inner disc and the external disc. The most frequent solution are the second and the third one, while the first is used for very special application. For example, in this image, you can see an impeller that is called the Barsk impeller, that is specific for very low flow and high head. Here you can see a shortcut of some typical impeller. Let's start with the enclosed single suction radial impeller. This is proper to handle a high head application. Usually it's used to when no strong constraint of suction capability is required. And if properly designed, it's a very efficient solution. This component is naturally unbalanced in the axial direction. So in some application, balancing holes are provided to reduce the axial thrust. Enclosed impeller require wear rings, usually mounted at the front and on the rear side. If needed, the external diameter of the impeller can be trimmed to reach the rated performances. Here we have the enclosed double suction radial impeller. This solution is used when the MPSH available on the plant is very low. It's composed by two suction impellers merged back to back. There are mainly two solutions of double suction impeller that can be realized: the symmetrical and the staggered. The symmetrical is the figure on the left, and the staggered is the figure on the right. The first is proper of low energy pump, and has a high efficiency. While the second one is used for high energy application because to stagger the impeller helps to reduce the pressure pulsation of the pump. And due to the increased wet surfaces of the inner disc, the solution is just a little bit less efficient. The double suction impeller is usually balanced on the axial direction, and it's used to handle very high flow rate. Replaceable when rings are mounted on both the impeller sides, and this configuration is placed on between bearing pumps, and also in this case the external diameter can be trimmed to reach the rated condition. Here we have the semi-open and open and enclosed impeller mixed at axial flow. This solution is typically used on vertical pumps and is proper to handle very high flow rates with low head. If we have API application for the pumps, in this case we mount a bearing just upward the impeller inlet, so the between bearing configuration shall be provided. Balance source can be used to reduce the axial thrust if needed. This solution has very limited trimming of the external diameter of the impeller due to the prevalent axial shape of the mineral channel. So let's talk about specific speed. Fundamental parameter that is used to identify pump hydraulic is the specific speed. It's defined as NS equal rotation velocity of the pump multiplied square value of the flow rate for each side. So if we have a double suction impeller, we must divide this term per 2. And also all divided for the upper stage of the pump with exponent 0.75. It's important to highlight that this number refers to the best efficiency point of the pump. As shown in the sketch, low specific speed in the left have a predominant radial shape of the impeller and is able to handle low flow rate with high head, while the high specific speed on the right of this plot has a predominant axial shape of the channel, and in this case it's able to handle a high capacity flow with low head. And if we use an international system unit, 1 meter cubic per hour of the international system is equal to 51.5 NQ for the imperial system. The NQ directly affects the efficiency of the pump due to the best interaction between impeller and volute. The highest efficiency can be achieved for NQ from 40 to 50. For lower NQ that are in the left part of the sketch, the efficiency decreased due to the friction and volumetric losses. While at high NQ that are in the right of the sketch, efficiency decreased to the impeller losses. Now let's talk about the outlet casing. In this component, the kinetic energy of the impeller must be converted partially in pressure energy, and this should be done in the most efficient way possible. There are mainly two types of outlet casing that are the most used. And there are the volute one and the diffuser one. The volute casing potentially can have the highest efficiency. Usually, it's a large component that allows to forgive contaminants, and it's resilient to off-load conditions. That means that the efficiency curve is quite a flat curve. Otherwise, the diffuser is a typical solution for high pressure application, and it's more compact solution compared to the volute. Sometimes a pump can have both the solution mounted together, but it's a very rare request from the customer. So we go just a little bit deeper on these two configurations. The volume casing potentially can have the highest efficiency. Usually it's a large component that allow large part to pass through the pump. There are different kinds of volute, and the most common are the single, used for low energy application, and the double, that is used for high energy pumps due to the radial thrust lower than the single one. Volute casing can be mounted on a single stage and on a multi-stage pump. The diffuser, due to the high number of vanes, it has the lowest radial thrust. And if properly designed, it can reach high efficiency, but the casting process is more complicated than the volute casing. The diffuser can be vaneless or vaned, and it has a return channel duct. In this figure, you can see the diffusing part on the left and the return channel part on the right. This solution is typically used on high-head OH2 units and multi-stage pump, and also in some vertical pumps. Okay, before going deeper on the explanation, we must recap some terminology that describe the main parameter of the centrifugal pumps. The flow is the quantity of fluid that passes into the pump in a time of unit. The pump application due to the fluid incompressibility. For pump application, we talk about volumetric flow rate. It's typically expressed in meter cubic per hour in SE units or gallon per minute in imperial units. The head is the quantity of fluid that passes into the pump the head is the height that the pump can move a fluid against gravity. It's expressed in feet or meters, and respectively for imperial or metric units. MPSH is the net positive suction head, and is expressed in feet or meters and can be mainly divided in MPSH available and required. The first is the MPSH available from the system, while the other is the MPSH required by the pump. Speed is the revolution per minute of the pump rotor and is expressed in round per minute or RPM. MAWP is the maximum allowable working pressure for the vessel or for the casing, and it's expressed in pound square inch or bar if you use imperial or metric units. And density is the mass amount per volume of the fluid, and it's measured in Liber to inch cubic or kilogram to meter cubic. Now we have very brief recap of the theory. As already described, the pump converts rotational energy into fluid flow and ultimately pressure. The equation below helps to explain the basics operation for a theoretical system. The continuity says that in a closed system, the entire entering mass is equal to the outlet mass. So for an incompressible liquid, the area per velocity at section 1 is equal to area per velocity at section 2. The second equation is the Bernoulli equation that says that the total energy of the flow without losses or external sources remain unchanged. This can usually be written in the way pressure plus dynamic pressure plus geodetic pressure constant. And a simple explanation is shown in the schemes in the bottom. On the left, we have a system with zero constant, with zero flow. The fluid on all the vertical tubes is at the same level. This is some manifold tube that have that are open to atmospheric pressure. On the right, we have a system with non-zero flow. The level of the fluid on the vertical tubes changes due to the effect of the velocity on the bottom. Higher velocity corresponds to lower level. The last tube on the right corresponds to the definition of the total pressure. It's similar to a pitot tube. And this is the maximum level that the maximum elevation that can be reached. So let's talk about the efficiency. Efficiency is the ratio between the useful power transferred by a centrifugal pump to the fluid to increase its pressure and the power that the pump absorbs from the driver. Keep in mind that the power is the largest total cost of most installed pump system. And for example, in some heavy-duty application, pumps needs over than megawatts to operate. The main items that contribute to the efficiency of a machine are recirculation, noise, vibration, hydraulic design, operating point, and also mechanical parts like seals or bearing or auxiliary. On the right, we have a typical performance curve. And best efficiency point is indicated with a triangle, and in this case is equal to 72%. If you zoom this part, we can see that near this point we have some ISO line in purple that refers to the ISO efficiency of this pump that can be reached by moving back and forth on the same curve, or can be reached also by trimming the external diameter of the impeller. So let's talk about the cavitation. We must remember that the pressure inside the pump changes due to energy conversion of losses. When the static pressure drops to the fluid vapor pressure, a bubble filled with vapor is formed due to the velocity increase in a given flow area. And this is the cavitation. As the vapor bubble moves to the region where static pressure is higher than fluid vapor pressure, the vapor bubble condenses and collapses immediately. This phenomenon generates a shock waves and a high pressure impact on the impeller surfaces that can cause material erosion and also damage. The entity of this impact is linked to the strength of the energy and on the dimension of the cavitation bubbles. And typically, there are several ways to mitigate and avoid this issue. For example, to use special material for the impeller and so on. As we already seen and said, that strong cavitation can seriously damage pump, mainly impeller, or valves. And here we can see some effect of cavitation on impeller blades for an open impeller or an enclosed impeller. Cavitation can be identified also by the following aspects. The head curve decreased, and the noise of the pump increased. The vibration signal has a wide broadband noise shape. Trillium is able to perform cavitation analysis by means of numerical tools that are shown in the image on the right, in order to estimate the suction capability of each kind of pump. As previously mentioned, the NPSH is the net positive suction head, and is defined as the energy at the upper impeller eye inlet minus the vapor pressure of the fluid at the specified temperature expressed in head. We need to make some clarification between the NPSH of the pump, which is necessary in order to partially suppress the cavitation. This value is the recommended NPSH, which describes how high the total head at pumping reference level should be so that the pump can operate without unacceptable or dangerous consequences. In this slide, there is an example of MPSH calculation. The scheme of the plant in the right is composed in this way. We have a pump that handles the fluid from a reservoir that is located at a certain elevation. The reservoir is open, so we have the atmospheric pressure on the free surface. The hypothesis is that the velocity at the inlet is negligible, so we don't consider the dynamic parts of this energy. The input data are the vapor pressure of the fluid that is equal to 0.032 bar, the density that is equal to 1000 kilo per meter cubic, the elevation of the tank that is 6 meters, and the friction losses on the suction duct that are 0.3 bar. If we make the substitution of all these components, we can have that the suction pressure at the impeller center line is 1.59 bar. If we reduce it by the pipe losses and by the pressure vapor, we can calculate the MPSH available on the plant. That in this case is equal to 12.8. So more in detail, MPSH required is the MPSH required by the pump to reach a typical behavior. There are several acronyms that can be applied to it, and each of these have a specific meaning. Typical, they are MPSH 3%, MPSH 1%, MPSH 0%, MPSH 40K, and MPSH incipient cavitation or cavitation free. The last one corresponds to the MPSH required to have no appreciable cavitation on the impeller. The MPSH 0% is the lowest value of the MPSH that still guarantees the head to remain unchanged. The MPSH 40K is the value at which the impeller will have a 40,000 hour life, while MPSH 3% and 1% are the value of MPSH where the head dropped respectively to 97% and 99% of head at zero cavitation operation. We must keep in mind that MPSH 3% is the usual measure for the industrial application, while in some cases the MPSH 0% is used for high energy application due to the cost reduction of the test. In the graph on the right, we can see a typical test of MPSH. This is called the pressure drop test. At a given flow rate, the MPSH available on the test bed is reduced until some of the MPSH characteristic occur. At first, we will encounter the MPSH incipient cavitation, but this value can be only measured through the visual observation of the cavitation level. And to make this, special equipment are needed. And this is mainly stroboscopic lamp and transparent window on the suction casing near the impeller in order to see the impeller, the bubble formation. By reducing the MPSH level, we encounter the MPSH 0% and MPSH 1%. And finally, we got the MPSH 3%. As I have seen, this graph is called the pressure drop test, and it should be repeated for each flow rate in order to characterize the suction capability of the pump by means of the curve flow MPSH.
I will be continuing the presentation, and what we will talk about in the next few slides will be how to read a pump performance curve And we will also talk about the elements contained within a pump performance curve. So we will begin in this slide talking about the duty point. And so the duty point represents where the pump will operate within the pump performance curve. As you can see listed in the slide, the duty point is composed of the head and flow. It is typical to see the duty point represented by a triangle within a pump curve. And the way that this point is plotted within the pump performance curve is simply by taking the head and flow value and plotting the point where these two meet. Notice the scale location for the head is located towards the center left of the figure, whereas the flow scale is located towards the bottom center of the figure. And if we were looking to find the duty point on any given pump curve, we would simply follow the duty point either horizontally to the left for the head or vertically down for flow. Now in this example, we can see that if we follow the duty point towards the left and meet the scale at the left, we run into the value of 48 meters of head. And if we follow the duty point towards the bottom, we see that we fall in the 70% range of flow. So this is how you would go about reading that duty point. Notice in this example that there's a black curve shown in black sitting below the performance curve where the duty point sits. This curve represents the curve associated with the minimum trim diameter of the impeller, and the upper curve, or where the duty point sits, is associated with the maximum impeller trim diameter. We will discuss this a little more in detail in the upcoming slides. So next, we'll move to the next slide, in which we will talk about MPSHR. So, as you may recall from Regis' explanation earlier, the lowercase r in this case stands for required, so MPSH required. And as the name applies, the MPSHR value is the minimum head value that the pump requires at suction in order for the pump to operate without any cavitation. Again, as Regis explained in more detail earlier, the MPSHR value is inherent to the pump and is determined by the pump manufacturer through testing. Notice the scale location for MPSHR is towards the bottom left of the figure. Notice also how its curve rises as the flow rises. And so similarly to the duty point, the way we would go about reaching the MPSHR value would be similar to how we covered in the last slide, which would be simply to follow the duty point down until we meet the MPSHR curve. Then we simply slide over to the scale to read the value. We can see in this scenario that the value at the rated duty point for MPSHR would be at around 3 meters of head. So we've added some illustrations within slides just to show, how you can draw lines within the curve and be able to locate the value much easier and read the value off the scale much easier. So moving forward, we'll talk now about power. So the power curve in this case is located towards the top of the performance curve, and the power scale location is towards the top left of the figure. Like with MPSHR, a curve is plotted in the power scale, and this curve represents the power absorbed by the pump as it operates through its performance curve. Similarly, as we did in the last slide with MPSHR, to read the power value, we simply follow the duty point upwards until we meet the power curve. Then again, we simply slide over to the scale to read the value. We can see if we follow the red dashed line there, the power being absorbed by the pump at this duty point is at around 13 kilowatts. So next, we will cover efficiency. Efficiency can be shown in two different methods. One is by plotting the trim-specific curve, or the efficiency curve for a particular impeller trim diameter, as we can see in the figure shown there. And another method would be to show ISO lines. We saw an example of this in one of Regis' slides earlier. And again, we're presenting the same slide here. So the difference between the two is that, as you can see within the isoline method, the value is called out at the point where the isoline meets the pump curve. Whereas in the trim-specific curve, we simply follow the same method as we did in the previous slide, where we follow the duty point up until we meet the efficiency curve. Now, notice in the figure to the right, the efficiency scale is towards the center right of the figure. And similarly, if we followed the line towards the scale, we would come across a value of 72%, just as it is called out in the example to the left. So one thing to point out about this point is that this particular efficiency point is also known as the pump's best efficiency point. And this is a value related to the flow point at which the pump is operating at its peak efficiency. And as you can see in both of these examples, this is exactly where the pump is operating. So next we will cover the terms of shutoff, runout, and MCSF. So shutoff is when the pump is operating with a closed discharge valve or at zero flow. Runout is essentially the opposite, where the pump is operating at the maximum flow it can reach. The minimum continuous stable flow is a point somewhere between shutoff and runout. And this is typically dictated by the pump manufacturer, just depending on the pump. And as the name implies, the MCSF, or the minimum continuous stable flow, is the minimum recommended flow a pump should be operated at in order to avoid cavitation and other potential issues. The following slide, we will talk about the parameters of allowable operating region and the preferred operating region. So the allowed operating region is a range in which the pump can operate to stay within the specified vibration limit. And in this figure, we can see that the allowable operating region is bound by the red dashed lines. The preferred operating region is a region in which the pump performs at or very near its best efficiency point. And as we discussed earlier in the figure, talking about efficiency, the preferred operating region is shown in this case by the highlighted blue section. The way to know what these regions mean is to look at the legends shown there within the pump performance curve towards the top right of the figure. And for further reference, both of these parameters are defined by governing bodies such as the Hydraulic Institute and the American Petroleum Institute. And they are there mainly to ensure that the pump is operated with the parameters that will not damage the pump. So now we move forward to the last part of the agenda, in which we will talk about basics to consider when selecting a centrifugal pump, and also some ways pumps can be arranged for to achieve various different performances. So in this slide, we will talk about end user information required before selecting a pump. Here we have listed a few key pieces of information for reference. However, I will go over some that I believe are essential to communicate to the pump manufacturer. We will begin with the performance need. This will communicate things such as your flow, your head, your system MPSH, or the MPSH available, as we did cover in more detail in his presentation within the earlier slides. And we can also communicate things such as the efficiency requirements and any power limits that may be present. So essentially, this is the same thing as communicating your duty point to the pump manufacturer. So then we have the pump fluid. This would be important to communicate, as it would help in the selection of materials for the pump. And it would also communicate important information such as fluid vapor pressure, viscosity, and the density of the fluid. Now, I would touch a little more on the density of the fluid, as density is associated with with a parameter known as specific gravity. And a specific gravity would affect the pressure of your system. So the higher the specific gravity of the fluid, the more pressure would be in the system. Vice versa, the lower the specific gravity value, the less pressure. And so this would be a good thing to keep in mind, when going about calculating your duty point, as pressure is not equivalent to head. As the head in your system would be the same regardless of the pressure. So just a good thing to keep in mind. Another point is another point would be any restrictions that you may have within your project, and these can range from pump speed, power absorbance limitations, minimum efficiency requirements, and costs, just to name a few. Again, these would be important to communicate as they all contribute to the pump selection process. Moving further down the list, we come across lead time requirements. So these are very important to communicate, as it would help the pump manufacturer know whether to go with the off-the-shelf pump, or if it's a new construction project, where a more specifically engineered pump would be required. The lead time may extend anywhere between months to a year or two, just depending on the project. And lastly, another important factor to communicate would be the driver. So this would be important to communicate because it would affect the pump package design, as a pump manufacturer would need to determine the coupling type, and also it would come into play with calculations should a factory test be performed at the factory on the pump. So next, we come across selecting the actual pump. So once we have come to the point where we calculate the operating parameter, know the system duty point, then comes time to look at manufacturer's pump curves. So this is where you would plot your system curve against the pump curve, with the goal of selecting a pump whose curve intersects your system curve at the calculated duty point as seen in the figure. However, there's a little more when going about matching the pump curve to your system curve. If you recall, we talked about the best efficiency point earlier in the presentation. Well, this is where that piece of information would come into play, as you would preferably want to select a pump whose best efficiency point matches your system duty point, or at least matches it as close as possible. Now, keep in mind that every system curve will be different depending on the application. So if it comes to the point where you cannot find a manufacturer within a manufacturer's catalog a pump curve that matches your system curve, then you can request from the pump manufacturer curves associated with a pump running at different speeds, or performance curves associated with the reduced impeller trim diameter, as we can discuss in the next slides. So here we see a slide in which we see different performance curves associated with a change in the impeller trim diameter. As you can see, these are known as using the equation shown in the slide is known as using the affinity laws. So the affinity laws tells us that a pump's capacity, head, and power can vary with the change in either speed or impeller trim diameter. The example we're seeing here is an example of curves with the change in diameter. However, similarly, we can achieve the same by reducing the pump speed, as we can see in the next slide. In this slide, we see curves associated with the reduction in speed. Similarly to the other example, reducing a pump speed can help you achieve various different duty points within your system. Now, a drawback to reducing either the impeller diameter or the speed would be that your efficiency would reduce, which may not always be the ideal thing to do, right? And so with that, we will move over to our Q&A session. If you guys have any questions, please feel free to post them in the chat. I want to thank everyone for showing up and for attending the webinar. Should you guys have any questions about any of the Trillium products, feel free to leave your information in the chat box and we can have one of our sales rep reach out to you. And again, thank you very much for attending, and we will move on to some questions. I have prepared, just a few questions that may or may not have come up within anybody in the audience, but one question is, what are the most common problems associated with centrifugal pumps? And just to name a few, these could range anywhere from your pump running dry, pump cavitation, pump seizure, galling, alignment issues, vibration, mechanical seal failure, low or undesired efficiency. And these are some of the most common problems associated with centrifugal pumps. Another question would be, what affects the efficiency of a pump? So in this case, we have surface roughness. As you can imagine, as the internal diameter of a pipe wears out and rusts out over time, the surface becomes a lot more rough, and this in turn affects the efficiency of a pump. Then we have internal clearances. These can be clearances within bearings or wearings, or even the impeller overall diameter within its casing. We also have things such as sudden expansion and contraction within the system. We also have sharp turns in the piping system. And also we have mechanical losses such as those associated with bearings, lip seals, mechanical seals, and packing. So Luigi, would you want to go ahead?
I want to add something about the polishing of the surfaces. Roughness is a very important parameter for the reach a good efficiency on the pump, because it acts on the friction losses of the pump. So a good casting quality is the target, the goal to have a very high efficient pump. But this is mainly true when we have little size pump, very not big pump, because in the case we have a big pump, the roughness effect can be more or less negligible. So roughness, yes, is a very important parameter, but we have to keep in mind that it's very important when we have a very little size pump.
There's a question that says, how do we calculate friction losses more practically?
Friction losses can be evaluated by some formula, some numerical correlation, but we prefer to evaluate the friction losses on pumps by using CFD tools. We have a big experience on using CFD tools. We use it for the hydraulic, for estimating the hydraulic performance of the pump. We have a 15-year experience on it. So we calculated these the effect of friction losses at not only by perform the complete analysis of the numerical analysis of the pump. When you talk about the complete analysis of the pump, we talk about the complete pump from the suction inlet to the discharge outlet nozzle. All the leakage are calculated, all the balancing device are calculated, and so on. And in this way, we can reach a good level of accuracy on the estimation of the friction losses. So we prefer to adopt this kind of solution because we are more confident on the final results than using the correlation and so on. We can use it in a first approximation at the first for the basic design, but when we have to go deeper with the exploration of the friction losses, we start making CFD analysis that are high-level analysis.
Thank you, Luigi. So another question is if there are any disadvantages for a pump operating at maximum impeller diameter. And so one of the disadvantages that I can name is that should you require a higher operating point, should you require your pump to achieve a higher operating point, there would be no way to do this by say using that pump. You would require, say, a pump in series, a pump in parallel, depending on the application. And in this case, I've seen some specifications from customers say things such as they would like a pump whose performance can achieve, say, 10% more in the future, should we require it, or something along the lines of that. I don't know if you have anything to add to that, Luigi. Question is there any disadvantage for a pump operating at maximum impeller diameter?
The advantages for having an impeller at maximum diameter?
Disadvantage?
Yes, usually yes. It's advantageous because in this case we have the lower losses between impeller and volute, and the external and the higher diameter of the impeller are the design point of the machine. If we cut out the external diameter of the impeller, we increase some losses that are called mixing losses, and this is detrimental for the overall efficiency of the pump. It depends on the topology of pump. For some pump, the impeller trimming is not so bad for the efficiency, but for example, for multi-stage pump, impeller trimming is very, very detrimental for the efficiency.
So another question that I see within the Q&A is how to avoid cavitation.
How to avoid cavitation. You must keep in mind that if you want to avoid cavitation, you have to give enough MPSH available. As you can see in the pressure drop graph, that if have you seen the pressure drop curve that I have shown to you, the MPSH free cavitation is at a very high level of MPSH available. So it's normal that at normal operation, the pumps have some sort of cavitation, but this sort of cavitation can be managed by the normal impeller life and by the service maintenance and so on. The problem is when the level of the cavitation is too high. If we have a very high level of cavitation, so we are near to MPSH 3%, close near the MPSH 3%, in this case we have big problem on impeller because of erosion, because of damage, because of vibration, and so on, and noise and so on. So if we want to avoid or reduce the cavitation, we can make a good design of the impeller with that will be selected for a very low MPSH required. And this means that the impeller is able to perform the global performance of the pumps because the effect of bubble cavitation is not so intensive in the impeller. And the cavitation damage can be for sure used, can be applied. And the cavitation damage can be applied when we use some particular material for the impeller, for example, that are resistant on cavitation erosion.
Okay, thank you, Luigi. So we will cover one last question as we are running out of time. And this is why most pump curves specify head instead of pressure, and between those two parameters, which one should we pay more attention to? So I believe I covered this a little during my presentation, and as I was explaining, the reason why head is specified within a performance curve and not pressure is because pressure is dependent on the fluid's specific gravity. So for a pump, the head will always be head for a pump. In other words, the lift of the pump, the capacity of the pump to lift the fluid from, say, level A to level B will be the same for the pump. However, it's the pressure that changes within your system. As, say, you pump a heavier fluid such as seawater, the pressure would be more than if you pump a fluid such as a hydrocarbon to the same lift. Then the hydrocarbon would have a much smaller pressure than would the seawater. So I guess in this case, it would be a good thing to always check your system and pressure rating of the system, and ensure that if you're pumping a dense fluid, make sure that your system is rated for a higher pressure. Well, again, thank you everyone for attending.
Thank you so much, everyone.
Thank you, guys.